apply convolution neural network for 3D LiDAR data has the challenge. 3D LiDAR data is a sparse 3D data. The convolution neural network, very successful in the image, is for 2D data. But how can we utilize this success of the convolution neural network for the LiDAR data? Then people think about lots of the different solutions. There are multiple ways, right? So one easiest way is do some projection. I project the 3D sparse point cloud as like an image. Then we can utilize the convolution neural CNN layers, right, for this projected image from the LiDAR. To project images, there are different ways. For example, one approach is project to the front view. Last class, we talked about squeeze segmentation. They project into the front view. Because front view has one advantage is it can overlap with image. Similar like an image view. This is their advantage. We also talk about the disadvantage. Is the project to the front, right? You lost lots of the depth information. Even some approaches try to keep the distance or XYZ as the channel features. But one problem is about the object overlapping. Another problem about the scale problem. In the image, some object is really far away, looks big. But in the LiDAR, every object is in 3D dimension. So you really don't have this kind of the scale effect. So this is some of the challenges for the front view. So last class we talked about the squeeze segmentation. And back to the 2016, I do also has one paper talk about using the LiDAR project to the front view, then apply to the 2D folded convolution neural network. Because this is 2D inferences. Then based on 2D inferences, right, when they inference the bounding box, previously is 2D bounding box. Now they add another dimension. So you can inference the 3D bounding box from the convolution 2D. So this is their approach. So although it's projected to the 2D front view, but they still can inference the like the depth. So getting the 3D bounding box. So the paper name is called vehicle detection from 3D LiDAR using the FCA. This is a very early work, right, in 2016. Then we also can see other work. So for example, like this paper, deep convolution neural network for point cloud vehicle detection and tracking in driving scenarios. What this one did is using the LiDAR point cloud, right? They get maybe multiple images. One image talk about, one is range images. Range image talk about the distance. They also have another image is like reflective. LiDAR also have reflectiveness. If the signal is very strong, the reflectiveness is also very strong. You have different images, right? They try to use different images for a convolution neural network. And what they do is they actually have this kind of architecture. It's like a segmentation, right? This is encoder and decoder architecture. This is very similar to our previous squeeze segmentation. And you have the range view and the reflectivity view. And when they construct the loss function, after the deconvolution, right? Every deconvolution, they have a loss function. Every deconvolution have a loss function. Every deconvolution have a loss function. That means they have multiple level of loss function, try to improve the accuracy. And then they also do the clustering, then apply the enhanced common filter for the tracking. That's why this is paper talk about projection, segmentation, and tracking. Similar to the like Baidu's work we talked. Okay, any question from this two front view projection based approaches? No. Okay, then last class we also talk about the other type of the projection, right? Remember when we talk about the Baidu Apollo, the solution used in the Baidu Apollo. This projection is projected to the bird's eye view. The reason project to the bird's eye view because it's the navigation of the vehicle, right? The occupancy map is typically in the bird's eye view. Now you only need this kind of 2D bird's eye view, there you can navigate a car. In the previous class, when we talk about Tesla's solution, the 2D detection results also map to the bird's eye view. then they can navigate a car. So the bird's eye view is a natural view for autonomous driving. So that's why the last class we mentioned about the solution used in Baidu Apollo, projected into the bird's eye view, right? And they are not lost all the height information, right? What they do is bird's eye view. They have 2D images, right? Then then they can keep some of the hand-picked features, right? Like highest point, like the offset from the center, X, Y, Z, right? All these steps information, all things are embedded in the channel, but it's hand-picked some of this feature information as a bird's eye view image. In addition to Baidu's approaches, there are also other approaches like research papers. The first one is like object detection and classification in occupancy grid maps using deep convolution networks. Occupancy grid map is like the bird's eye view, because when you do navigation, you probably need this occupancy grid map. What they do is they first do the LiDAR to the multi-grid mapping, bird's eye view, but it's not one map. They choose multiple maps over here, multiple bird's eye view, but all the bird's eye view are 2D, so you can do the 2D detection. Then based on this 2D detection results, you can inference this 3D bounding box. Inference 3D bounding box. Then after you have this 3D bounding box, right, you can remap it to the front view. You can do the box verification with the 2D images, convert to the front view. This is not a sensor fusion, not fusion. They just verify with the 2D images. Try to improve the accuracy. So this is another paper. Okay. Another paper is called real-time 3D. They focus about the real-time detection. So what this paper did is they try to the projection approaches, right? Also similar to Baidu Apollo's approach, really suitable for the real time. They pick a vertical grid, put it into the bird's eye view, right? Then for every cell, they can pick some maybe max value, average value, or minimum value to do some encoding. This is also a hand-picked feature, similar to Baidu Apollo. Baidu Apollo using more features. They only using 3. Then project into this image. So max view, average view, and minimum value similar to images RGB 3 channel. Now this is similar. Then they actually have this kind of bird's eye view 2D image. Then based on this 2D image, then they can utilize the fast RCN type of the 2-stage detector. Feature extraction, region proposal network, get some ROI, right? Then they get the feature map, you can get the location, orientation, and the size of the object. Then finally, based on this 2D bounding box to inference this 3D bounding box. Because sometimes you also have the height information. You can inference the height information from the 2D extended to 3D. So this is a real-time 3D based solution. So you can see the key idea is very similar, but they applied a 2D detector over here, and their feature encoding, how they manually set the feature are different. Another paper is called BirdNet. From the net is they using the bird's eye view, BirdNet, 3D detection framework for LiDAR. What they do is based on the LiDAR point cloud, right? They do 2 steps. Because you can see from this LiDAR image, you can see this is kind of the LiDAR reflection is ground, and this is ground information. Right? When the LiDAR hitting the ground, they have lots of reflection. So lots of reflections are actually coming from the ground. It may impact the 3D detection. So what they do is they try to do the ground estimation, and they think that the ground estimation is pretty useful. Then another view is another part is LiDAR's bird's eye view. Now, LiDAR bird's eye view is similar to the other approaches, right? Get a feature map, like a 2D detection, 2-stage detector, right? RPN, region proposal network, get an ROI, then do the classification, right? Then finally, they do the post-processing, right? And in this step, they already can get the 2D aligned detection. In this step, you get the 2D detection, right? Then combined with the ground estimation, and the height information, you can inference this 3D bounding box. So the 3D bounding box also inferenced in the post-processing, similar to the previous approaches. But they separated the ground estimation. I try to improve this post-estimation. This is called BirdNet. This is another solution in the bird's eye view based projection. Okay, any questions for this 3 different solutions? This looks, the key idea looks very similar. Any other question? There are other bird's eye view projection based solutions. This one is pretty famous. Real-time 3D detection from point cloud. They called it using the pixel-wise neural network predictions. So what they do is they still do the bird's eye view representation, but their detector, they call it is oriented 3D object detector from the pixel-wise neural network prediction. So basically, this is they are not only predict the 3D bounding box, also predict the orientation, and it is a single stage, different from the previous one. Like you have RPN, this is just a single stage approach. Then they finally get the 3D bird's eye view detection. This is a very interesting solution. So then the other two solutions is applied YOLO. YOLO is a 2D detector. Using YOLO to extend to 3D. One is called end-to-end real-time 3D oriented bounding box detection from that point. So what they do is they convert it to the two bird's eye view. One bird's eye view based on maximum height. One bird's eye view based on the density. They have two images. Then they extended the YOLO V2, the loss function. Previous YOLO V2 loss function is just XY bounding box, but they extended the YOLO V2 the loss function to 3D bounding box with box angle, XYZ, and the height. So this is the key information for this bounding box. Bounding box also needed to have the angle. So previously in the 2D detection, there are also angle-based 2D detection. For example, previously, if we say all the bounding boxes are rectangle, we didn't apply angle for the bounding box, 2D detection bounding box. But there are some detectors you can apply the angle. You can have the box like this, have some better alignment. You also have some 2D detector like this. But for 3D detector, you definitely need to be aligned. That's why you need the angle and the bounding boxes, the 3D boxes, XYZ, and their height. This is minimum requirement for a 3D bounding box. So you extended the loss function. Previously, you only have the bounding box only have 4 elements. So x min, y min, x max, y max, or x center, y center, y center height. But now you have multiple. You have angle, XYZ, and the height. So extended. This is YOLO 3D. Another solution is called YOLO 4D. YOLO 4D is another dimension is time. They're not using a single frame. They utilize multiple frames. Basically, it's YOLO 3D. YOLO 3D plus a tracking. But the tracking, they're using LSTM for this tracking process. The architecture like this, right? So every frame go to CN. They have a convolution LSTM to do the tracking process. Where they utilize the multiple frame and the timing information. So that's why it is called YOLO 4D. Okay, any other question for these 3 solutions? And we have more. Bird's eye view, we have lots of solutions. This solution is also very interesting, called fast and furious. The interesting thing of this one is this is also bird's eye view detection, 3D detection. But what they do is they combine 3D detection, tracking, and motion forecasting together. So the network is not only do the 3D detection, they also can do the tracking and the motion forecasting. And they utilize the multiple LiDAR sports iframe using the time domain together, then do all three things together. So this is the most interesting thing for this one, is a multiple task together. Another famous paper is called the complex Euro. Now it's also a Euro-based detector. What they do is similar to the Euro architecture. They convert using the three bird's eye view, like a pseudo RGB map for the LiDAR bird's eye view. Then they create similar like a Euro's architecture. Previously, we mentioned the Euro architecture, they don't get the regional interest. Instead, they, for every cell, they do the encoding. Every cell, they do the encoding. The vector size for Euro V3 is 85. But for this one is they do Euro V3 is 3 detection per cell. But what they do is for every cell, they do the encoding, but every cell is 5 predictions per cell. They have 5 predictions per cell. So every cell, you have 0 to 4, 5 predictions. Then each prediction, similar to Euro, but Euro have object or not object, then have bounding box SYD, then have 80 classes. What they do is they have TX, TY, TW. So that means X, Y, Y's length, and the angle. They based on, they call it like using a complex number. You have the image part. So divided as the complex number. Then they have P0, Pn for all the classes. So that means each block's encoding. Then finally, based on this encoding results, they do the detector, get the 3D bounding box. So this is the complex Euro, extending the Euro architecture for the 3D. Okay, any question for this projection-based solution? Either front view projection or bird's eye view based projection. Any other question? Okay, then last class we already mentioned another solution is grid representation. One popular grid representation is using 3D voxelization process to the quantization of the 3D space. Quantify the 3D space as X, Y, and Z. Because this quantization process, you divide every cell, right? Then it's different from the 3D LiDAR is sparse. This one is if there's no data over there, you apply 0. So it's a dense representation. And this representation is like you keep the height information. So you can almost preserve the original point cloud information. Although this is still you reduce some of the points. If there are many points in one cell, you definitely do the downsampling. But you can keep this major points information in this cell. And because this 3D vocalization process, Vox representation is very dense. So this one can be utilize this convolution neural network. Because convolution neural network require a very dense image features. So this one can be easily applied the CNN. And so there are some advantages. So because they can transfer the raw point clouds into structured grid representation, and you can using the CNNs to do the object detection process. And compared to the range images, 2D representation, 3D vocalization process, do not suffer from scale ambiguity because it's still the 3D information is still there, occlusion because there is no projection process. The 3D information are still there. They didn't project to any 2D plane. But there are also other problems for this 3D vocalization process. Still lost some information, although it's a minimum loss. And when they represent the fixed size vector, when do the vocalization process, so every cell represents a fixed size of the vector. Definitely some information are lost. Another thing is LiDAR point has lots of, it's very sparse. There are lots of empty points, but the vocalization process is very, very dense. So they may generate more data. The generate the size may be larger than the raw point cloud representation. So this is a potential issue. The computation cost is pretty high. Because you need this, every grid has a dense representation. So this is the problem. Okay, so last class we talked about one of the breakthrough paper. The reason why we call it breakthrough because this one laid the foundation for many of the future work. Even current state-of-art solutions are all based on this architecture. And using vocalization-based solutions, they actually achieve the state-of-art based on the state-of-art accuracy. And the achieved accuracy is much better than projection-based. Because projection-based lost more information. But the vocalization process, at least they keep most of the 3D information. So this is a breakthrough paper. And you will find many of the recent architecture or learning this architecture. So this one is like a fast RCN or Euro in the 2D detection area. They almost this is a foundation for many of the future work. So this is published in 2018. It's a pretty new paper from Apple. One interesting thing for this paper is they propose a end-to-end deep learning architecture, right? And they can learn the 3D features from the 3D point cloud. It's not like previously, like when you do projection, you can set up manually features. These features is automatically learned. So last class we already talked about some of the basic approaches, right? The first step is they do the vocalization process. They using the Vox grid filter divided into the 3D space as voxes. Then they also do some. They also can change the vox size based on the subsampling rate. The VoxNet architecture has 3 components, and this 3 component is also the foundation for modern LiDAR-based detectors. Almost all recent LiDAR-based detectors based on this architecture. First one is the feature learning network. To get the features representation from the LiDAR point cloud. And then they have the conv backbone, convolution middle layer. Finally, they have the region proposal network to get the 3D bounding box. And the VoxNet paper, what they have is the feature learning network. You get a sparse 4D tensor. That's why this convolution middle layer is not convolution 2D. It's actually convolution 3D. They process the 4D tensor. Then finally get the 3D detection. So it becomes a generalized detection framework for the LiDAR point cloud. So for example, let's talk about the first part, feature learning network. This is also one of the breakthrough. Instead of using the projection, right, and pick some manual features, what they did is they tried to using a neural network process to learn the feature. So since they utilize the Vox representation, they subdivide the 3D space into the equally spaced voxes. So it's like D, H, and W. So along with Z, Y, and X axis. So this is the 3D grid, 3D voxes. Then inside every vox cell, they may have multiple points over there. Some voxes maybe have many points. Some voxes maybe like vox 3, maybe no points at all. So that's normal because many points, for example here, no points at all, no points at all. But this point, this cell has lots of points. If one cell has lots of points, we can lower the complexity. We can randomly sample a fixed number t. If they have more than t points, to do some down sampling, this is called random sampling. Then next step, next step is we want to do the feature encoding. Now, how we can encode the feature? Now, how we can represent this different 3D points? So what they do is they calculate the local mean as the centroid of all the points. So for all the points over there, they calculate the centroid. Then every point pi, then we also argument add an additional feature. The additional feature is a relative offset respect to the centroid. So every point, previously they only have a feature x, y, z, right? And now they also have additional feature is relative to the centroid inside this voxel. Okay, then they add more features, right? Previously only x, y, z. Now they have x, y, z, and relative to the centroid. More feature. It's like a point-wise feature. Then for every point, they go through a fully connected network. Do the encoding. Using this fully connected network to go to another feature space. This feature space may bigger. Go to the feature space. They do the mapping. Okay, then this is feature space, right? For feature space, what we typically do is we can utilize the high-level feature sometimes and do the fusion with low-level feature. What they do, they also have some fusion part. After they get a point-wise feature representation, right? They do elements-wise max pooling. Get some locally aggregated feature. And then argument each point with this augmented feature. That means this is previously one point only have their localized feature. Right now we can add do max pooling process, get the locally aggregated feature. Then locally aggregated feature can add back to the individual points. So individual points can have more feature. And this point not only have local feature, they also have global feature, nearby feature, contributed by the max pooling. Right? So this point has more features, right, than XYZ. Right? XYZ extended to the relative XYZ and relative to centroid. Then they also do fully connected layer, get the feature space. Then for feature space, localized feature space also aggregate the max pooling results. This is aggregated feature results. Okay, so this is become a new point-wise feature. And so every point you have this feature. Okay, any question for this feature encoding process? Any question? So previously every point only had x, y, z, right? And now do this kind of transformation. Make sure every point has like a feature list. Now not just x, y, z. Any question for this feature encoding part? Okay, then after this feature encoding part, right? So then they do the sparse tensor representation. Because there are many some voxels are empty. They only process the non-empty voxels. If it is empty voxels, we don't need to process. So they can list a list of vox features. And each uniquely associated with the spatial coordinate of non-empty voxels. Yeah, so previously you can see in the feature encoding part, we can get this point-wise features. Then they go to another fully connected layer. And also do elements-wise pooling. They get a vox-wise feature. Okay, this feature is not just represent each point; it represents the whole vox, and that means whole group, one feature list. Then, since there are some voxels, their information, some voxels are empty. They only select the non-empty voxels. Now, actually, you can return it back, go to the original 3D space. If some spaces there are points, they have this kind of fixed vox-wise feature representation. This is another feature representation. Now you can see this image is become 3 times D times H times W. Is a 4D tensor. So you get a sparse 4D tensor. So this is the feature representation process. This is also their feature learning network because they have multiple fully connected layers. This can be trained. So that's why this network itself can be trained to learn the features. Okay, any question for this feature learning part? Then after this feature learning part, right, they can have the convolution middle layer. Then this convolution middle layer, because this is a 4D tensor, they need to apply the 3D convolution. 3D convolution is a 4-dimensional 4D operation, just like a 2D convolution is a 3D operation. And they apply the 3D convolution layer, batch normalization layer, Lulu layer sequentially. This is similar to our previous 2D backbone. So the aggregate this Vox-wise features. And after they get the features, they need to go to the region proposal network. Region proposal network is similar to the fast RCN. They get the bounding boxes. Since it is only a one-stage detector, that's why the region proposal network can directly output the proposal. That's the bounding box. They utilize this proposal, the bounding box, as the final 3D bounding box. So their region proposal network looks like this. So they have feature in. So they have 3 blocks of the 4D convolution layer. First layer, downsample the feature by half, because they utilize the convolution with stride size equals 2. They do downsampling, downsampling. Then after each convolution, they actually also have this batch normalization and the Lulu operations. So this is block 1, block 2, and block 3. Then they also do the deconvolution. Deconvolution previously in the FPN. Now we know how to do the deconvolution because they can go back to the high dimension level. So this is, you can see, go to low dimension. Since but it's slightly different from the FPN. FPN, they do detect from multiple level of the features. What they do is they have convolution becomes more and small, right? Then what they do is they do the deconvolution, and deconvolution back to a larger space. This resolution is on only half of the width and height. It's bigger, but then add this channel accumulate them together. The reason why they're using high-level feature is because high-level feature has a better location feature. And that's why they're using this high-level feature aggregated into the high-level feature. But they also utilize the deconvolution actually from the deeper features. Then based on this feature, they have this 2 detection header. One is probability score map. One is the regression map. Regression map is get the 3D bounding boxes and the angle. So probability map get the whether there is object or don't have the object. So this is 2 headers over there. And you will find this region proposal network as a third stage also applied by many of the current solutions. They also using this topology. Yeah. Finally, the learning targets is probability score map and a regression map. One is the classification, one is the regression for the 14 elements. Probability map is just whether they have the object or don't have the object. Yeah. So when Vox data is published, right, it's they can be applied for more challenging 3D tasks. With some easy 3D challenging tasks, the projection-based solution is okay. But for some very challenging 3D tasks, they have 80% improvement compared with the bird's eye solution, and around 8 to 12% improvement, and it's actually represent the state of art of the 3D detection solution. One interesting thing that they proved that you actually can using the they can using the neural network to automatically learn the 3D shape information instead of using the handcrafted features. So this is the contribution of the FoxNet. So this is one of the breakthrough paper and almost lays the foundation of current modern 3D detectors. Okay, any question for the FoxNet? Any question? Okay, but the FoxNet still has lots of problems. Yeah, one challenge is they even don't have the official implementation. It's closed source. Apple maybe have their good implementation internally, but they didn't open source it. There are lots of the third-party FoxNet implementation, but they cannot really approach the accuracy of the official models from Apple. And in addition to this implementation, FoxNet also has other technical problems. So for example, the computational cost of the FoxNet is very high, especially the backbone utilizes the 4D tensor operation. That's 3D convolution. This is very, very expensive. Another thing is for some 3D boxes, if they are in opposite direction, if they are in opposite direction, because the car may be facing to you or maybe leaving to you, this is opposite direction. For this kind of cases, the 3D bounding boxes they have a huge loss. So that means that the loss function are not very good. So in some cases, they didn't work well. And then there's a very good work called second. It's called the sparsely embedded convolution detection. This is also a very famous, a very, very important work. From my own point of view, this is like the Euro V5. So because they set up lots of the implementation practice, how to implement the 3D detection. Many modern implementation, all based on the second implementation, and how they solve this loss function problem. They all utilize this second operation. Using what they did. So if we say FoxNet is the foundation for the theoretical framework, the theoretical framework is the foundation, modern detectors foundation, FoxNet. Then the practical foundation is second, because the second solved many practical problems in the FoxNet, and they open sourced the solution. So this is the good part that people try to learn how they implemented the code, and that's why you will see many of the latest 3D detectors, the implementation is very similar, and how they utilize the code, how they utilize dataset, dataset representation, all the things are very similar to the second. So second, in addition to the FoxNet, they added a direction classifier. They also learned the Vox features to the Vox feature extractor. But instead of using the 3D operation, they're using a sparse convolution layer. This is a new contribution. And the sparse convolution layer is actually pretty hard to understand. Previously, that's like the FoxNet or other 3D detector only have classify or bounding box regressor. They actually added another called the direction classifier. To try to solve the huge loss problem for the 3D bounding boxes. And you may wonder, direction is angle theta, right? Why it's not the direction regression? Why it is a direction classifier? Because angle is a value. Value it should be a regression, right? And why not put the theta into the box regressor? Why it is separated? You have a direction classifier. This is question mark. Think about that. Why? Why they have a direction classifier? So this is some of the major improvement of the second. So many future work all based on the second code. For example, in the future, like the point period, also based on the official code of the second. Although this link is stopped updating, because but many future implementation are all based on this kind of code. First, let's take a look at the backbone. Now we just modify. Yeah, we can see based on the VoxNet's paper. So feature learning network is similar. What they change is the convolution middle layer as sparse, using kind of sparse convolution layer. Sparse convolution layer itself operation is very complex. So let's skip from here. So and we just know it's a sparse convolution operation. For the region proposal part, but the backbone part is similar. Different array features aggregate them together, but they have the 3 header. Previously in the VoxNet, for 3D bounding box, we have X, Y, Z for the center of the 3D bounding box. Then Y and height of the 3D bounding box. So this is like the 3D bounding box size, and the angle is theta, the angle of the 3D bounding box. So we can using this 7 element to represent a 3D bounding box. And this 3D bounding box regression is kind of regression problem. For regression problem, we can using smooth L1 loss. So that's actually used in the VoxNet. Using smooth L1 loss for all these 7 elements as a regression problem. But the problem people find that if there are 2 bounding boxes, right? One is car facing to you, one is leaving to you. This bounding box for all the previous 6 elements, they overlap. XC, YC, ZC, L, W, H are exactly the same. So this 6 elements, the loss is 0. Actually, it's good. But for the theta, because the direction is inverse, the theta value is very, very high. Theta value, for example, is 180 degree minus 0. The theta value is 180, is highest. Then during the training process, you think, this model is not that good. Then you change the weights. Then make this part become worse. So this is a huge problem, because when this type of the bounding box happens, you only need to know what's the direction. But then it's a perfect match of 3 bounding box. But if you combine all things together as a smooth L1 loss, because the theta has a very high value, it will disrupt your training process, cause a lot of the problem. So what's the second? What they did is they try to add independent loss for the angle. The angle loss and X, Y, Z, L, W, H are different. They also using the smooth L1 loss because it's a regression. Regression we can use smooth L1 loss. But instead of directly utilize like 180 degrees kind of number is so big, using this sine value. And when your sine value is from 0 to 1, it makes the value limited. That's much better. And if the theta is very close, if the value is very close, or if they have pi 180 degree difference, the loss equal to 0. So this new added loss function for angle is good. So if the angle is very, very small, or they have 180 degree, the loss is 0. So the loss is good, but the problem is they also have some ambiguity. But so either 0 or pi degree, all have the loss value equal to 0. So you need to classify these 2 cases. To classify these 2 cases, that's why they add a direction classifier. So it's not a direction regressor, it's a direction classifier to classify whether it is 0 degree or pi. So this is the reason why they add another direction classifier. Remember, it's not a direction regressor, it's a classifier. And this setup is also used in many of the modern 3D detection works. So this is one of the major contributions for the second. Any question for the second? Yeah, that's why they have classified both regressor and the direction classifier. Yeah, if you want to learn how they implement, right, you can check their official code. So this is like the particle foundation for many of the famous work. Okay, any question so far? VoxNet second, any other so currently we finished the projection to front view, projection to bird's eye view, and the Vox representation. Yeah, so two major work. One is Apple's VoxNet, then we have second. This is some of the major VoxNet representation kind of work. Okay, then we can talk about another work. Now, another work is a simplified VoxNet. Or what we can see is a simplified second. Previously, we have the Vox representation. Vox representation is in the we divide the whole space as a 3D. So whole space is vertical and also have this horizontal. So we have lots of the grid. Now 3D grid. A 3D grid has one challenge is it's so big, and it's pretty complex. So one simplified version is in the vertical direction. Instead of using multiple Vox cell, only using one Vox cell. And this kind of Vox cell is called pillar. That means vertical, there's only one cell. Vertical, only one cell. And that makes things simple. But how you can learn the feature, the points inside this pillar. This is similar to the previous, either the VoxNet and the second. They also can try to learn from these features. So this is called pillar encoders. Pillar encoder you also can using hand engineering the feature, hand pick the feature. Like this one, pixel. This one, pixel is actually you can see this kind of pillar encoder, hand pick the engineering pillar encoder is very similar to bird's eye view projection. Besides bird's eye view projection, we also have a vertical pillar. Right, vertical pillar not just compressing into a 2D image, they also can get some features from the height. Like Baidu's approach is also a similar kind of the pillar encoder. But the second type of the encoder is you can use the machine to learn the feature representation, feature encoder. That's another famous approach called the point pillar. Point pillar, very interesting. So previously we can see their implementation is even merged with the second implementation. Now, although they originally have their own implementation, right? But they merged to the second implementation because they actually learned lots of the implementation from the second. So actually, this approach is based on the second. That's why they actually can merge into the second as official implementation to have these two models together. And particularly is coming from a company. Second is coming from a professor in Chongqing University. Is like Yan Yan in Chongqing University. He's from academia. He's a professor. Although he's not from a very famous university, but his work actually really good. Then some company, for example, Notomi is a kind of Aptiv company. Aptiv, you know, is they do autonomous driving systems, right? It's also a vendor for many companies, right? So the engineering from this company, they actually can learn from the second implementation. but they want to do a engineering the approach suitable for real time. Simplified second. So second is a 3D Vox representation. They want to represent it just using the pillar. But the other part can be similar. So using the vertical column direction. But the feature can also be learned from this vertical feature. This kind of approach is like it's similar to the actually. This looks like combined with the bird's eye view projection with learned feature from a pillar, from a Vox. They can apply the traditional 2D convolution layer, similar to the bird's eye view projection. So 2D convolution layer can be applied. You don't need to using the 3D convolution. Don't utilize the sparse convolution used in the second. They can just using the 2D convolution. Although the performance can be slightly dropped, but it's very practical. The point pillar, the good thing is about it's very high speed because it's coming from one company. It's very high speed. And the accuracy is also pretty good, although it is lower than second, but it's significantly better than other projection-based solutions. So this is a good thing for the point pillar. Because it's very practical. And it's very, very fast, suitable for the real time. That's why if you have some practical project want to implement the 3D detection, then the point pillar is a good starting point. So now let's take a look about this point pillar architecture. Because the learn feature on pillars is like vertical column. This kind of the vertical column. So the first step is discretize into evenly graded grid in XY plane, not XYZ. Because in the Z plane, they only have one pillar. So it's only in the XY plane. So the points in each pillar, then do some argumentation. This is similar to the VoxNet. But the VoxNet only with all the points center. They not only using the points center. This is calculated based on like all the points in this pillar. This is center. This is relative to center. In addition to this, they also add elements to XP and YP. XYP is the pillar's XY center. You also add an offset for XP and YP. So previously the point is X, Y, Z. Now how many features for each pillar? X, Y, Z, theta. No. X, Y, Z in density. X, Y, Z in density. Now the argument is X, Y, Z, C and XP, YP. Now together they have the 9-dimension feature. They have more features there. So this is the first step. Get the representation. So now D is like a 9-dimensional feature. D is feature dimension. The D. D is so D looks like a images channel, like RGB channel. D is actually 9. Then we also have P. P is we only need to pick some pairs with non-empty points. P is a non-empty pillar number. This is like total number of the pillars. P. Then every pillar has multiple number of the points. So N is points in one pillar. So that's why after you do this encoding process, you convert the point cloud to a 3D tensor like D, P, and M. D's dimension for features dimension 9. So D is feature dimension 9 over here. Now P is a number of pillars. So that means every like this kind of direction, every this kind of cubic is for one pillar, right? Because P is for dimension of the pillar, pillar index. This is pillar index. The N is for number of the points in one pillar. So this is called the stacked pillars representation. This is the first part. Second part is they want to learn the feature. Finally, after they learn the feature, it becomes 2D. How they can learn the feature from the 3D space to this 2D. So now we can actually check one recent implementation, because the original implementation, their company's original implementation is not updated. They merged into the second implementation, but the second implementation also didn't update for more than 2 years. Around the recent 2 years, there's no update. So that's why we didn't utilize this two original implementation. But instead, there are some recent approaches from the OpenMM lab. They try to propose some generalized 3D detector framework. In the 2D detection part, we know MM detection 2D. The same lab, actually, they also have the MM detection 3D. And they also have the open PC detection. Because this two, similar to detection 2 and the MM2D, this is a two general framework for the 3D detection. And that's why we based on this two code. I also have the fork of my versions. I do some changes. First, like the MM detection, it's very hard to install because you need to combine lots of the CUDA library, CUDA packages, and lots of the 3D operations. They have C++ in the CUDA. You need to do the compile into the library. It's pretty hard. Then you can utilize my forked version. The original version do not work in over HPC, but my forked version works in over HPC. Then in the HPC tutorial, I also have very detailed step for how to utilize MM detection 3D. How to install the MM detection 3D in over HPC tutorial. Now you can see how we can install MM detection 3D in over HPC. You can just follow my step. But you need to using over forked version. The original version cannot work in over HPC because of different library dependency. Then in addition to the original MM detection 3D, I also added the Waymo KT based detection. The MM detection recently also has support Waymo, but their Waymo is different. They create a new dataset format using the original dataset format for Waymo. My Waymo implementation added into the MM detection 3D is follows the same representation format of the KT. So that makes things easy to understand. So you can learn from the basic KT dataset. Then I also converted the Waymo into the KT format. Then you just change it, the dataset class like Waymo KT to make it easy switch from KT to Waymo KT instead of using their provided the Waymo implementation. But if you want to utilize their implemented Waymo detection, that's also fine because it's already there. Similar things in the open detection. Open detection, I also added the Waymo KT 3D and added lots of comments. You can see my forked version. But unfortunately, open PC detection, I can install it in my local computer because they require a sparse convolution library. The sparse convolution library, they have some bug, but now the bug is fixed in the CUDA 11. So if you have CUDA 11, you can try the open detection. Has no problem. But over HPC only have the CUDA 10.1. Yeah, you can try if you are interested. Try to install the open PC detection in HPC. But at least when I tried, I didn't make it work. So that's why for this version, it's in my local computer. But the MM detection, yeah, I can work in the HPC. Okay, so now we can simply utilize these two implementations are similar. Now MM detection 3D support it's more complex, support more models. There are lots of the modern 3D detection models all available there. OpenPC detection is simple and easy to understand, but they have less number of the models supported. It's based on your choice. Which one? You want to more complex, more advanced models? MM detection 3D. If you want using HPC, MM detection 3D. If you have your localized computer, Colab, you can have CUDA 11, or you want to understand the code, you want to make have an easy to use framework. That's OpenPC detection. Okay, now we can utilize the code in the OpenPC DT and map with the Point Pillow's original papers architecture, so that we can have a better understanding, because we can map the code, and then we can learn from this architecture to understand why it looks like this. Otherwise, we have no idea what they did, coming from there to there, how they do the detailed steps. Okay, now let's take a look about the detailed code. The implementation is based on the PyTorch. PyTorch dataset, they always has the get item. It means you can fetch a batch of data or fetch one item of the data from dataset. So in the dataset get item, now you can using NP NumPy and read the file. The KT file is actually in the bin format. You can read the LiDAR points. LiDAR points is this is how many number of the points you have. This is 4. And this is features for the original points. Features for original points is X, Y, Z, and the intensity. This is four features of the points. Then after you get the original LiDAR, they also have the prepare data operation. The prepare data operation actually call a dataset template. Under this code, you have the prepare data function. This prepare data function, they do two things. One is point feature encoder. Point feature encoder, what they do is they do absolute coordinate encoding, using absolute coordinate X, Y, Z. And sometimes the different LiDAR format, they have different X, Y, Z. You can do the absolute coordinate encoding. So after you do this absolute coordinate encoding, the size are same. So meaning are same. Still the total number of the points, X, Y, Z, in the absolute coordinate and the intensity. So this is absolute coordinate encoding. Then finally return a value is a dictionary that have points. So this is absolute encoding. So this is the total number of the points after the absolute encoding. Then they do the second step. After the point feature encoding, they have second step called the data processor forward. Data processor, what they did, they also inside this data to the Python file. Data processor forward, they have a class, is the method, the actual method is in the class data processor. For the data processor, they can attach multiple processors there. And you can specify in the configuration file. Here, what they have is processor. They have 3 processors. First processor is mask points and boxes outside range. That means the points may coming from maybe 100 meters away. But for example, we only need to cover maybe 60 meters or 70 meters. So you need to remove the points outside of your interest range. So in the configuration file, you can set up this kind of vector. Now this means the X range from 0 to 69.12 meter. So almost 70 meters in the X range. And based on the validized coordinate in the KT, X is facing to the front. So that means facing for the front from 0 meter to 69.12 meters. The Y range, Y is the left and the right side, in the left side. So you can have the minus 39 meters to right side, 39 meters. This is the Y's. And height is the Z range. Is the Z range. Z range is -3 meters to 1 meters. The reason why -3 meters, because the LiDAR is sometimes in the top of the vehicle. That's why you have -3 meters and top 1 meters as Z range. So here you do the mask point outside of the range. But in the actual code, they didn't do the mask for the Z range. They only mask for X and Y range as the coordinate. With the point pillar, the vertical range you don't need to filter out. They only filter out the X and Y. So this is the first step to the mask. So after filter out, you will find the point number dropped from 113K to 61K. So the points number dropped. Then you can shuffle point, but this is only used training. Shuffle some of the point, because shuffle the point doesn't impact anything. Third data processor, this is the vocalization process. Transfer the points to voxes. Although it's a point pillar, but the point pillar is also kind of the vox representation. The only thing is the Z range, you only have one vox. So vox generator is actually using the library, the sparse convolution library, to get the vox representation. Then the final results return everything in a data dictionary. You have original data points. It's a filtered data points. This is 4 elements. The current frame ID. Voxes. Voxes. This is the number of the voxes. This is total number of the voxes. 32 means the maximal features for this voxes. The maximum points for this voxes, right? It's like n number of the voxes. Now there's maximum points in this voxes, and the dimension is 4. And you also need to record the vox's original location, the coordinates. So that's why you also have a vox coordinates, right? n times 3 in the ZYX format. ZYX, the vox's ZYX format. So this is the size. And you also have total number of the voxes. So this is the data set you get. Get the original points and the vox representation. All the points. So this is in the data processor. This is previous step. You get the data, and they have another step is the correlate batch. What they do is do the padding in the left for the points and for the voxes. So they become this kind of the dimension. This is the data we provide. Next step is really go to the model, model forward. Then this is actual class point pillar model. And the point pillar model, they actually has 4 major components. One is the pillar VFE, is the vox feature encoding. Encode the feature. Second step is the map to BEV module. Is the point pillar scatter. It's mapped back to the bird's eye view. Then they have the backbone 2D. Finally, they have detection header to detect the 3D bounding box. That's why they do the for loop for this 4 different modules. Now we can take a look modules one by one. First, we do the VFE, vox feature encoding. So from this part is the vox feature encoding is the previously you have the DPNN. So what they do is they want to have a linear layer is applied by batch normalization and loop to generate a CP and N sized tensor. Then they have a max operation over the channels. Then they can get the C and P. This is the C and P. So what's the detailed process from this feature learning? How you can get the DPN tensor become a CNP tensor. So we can check the code. For the that's the first step in the pillow VFE Vox feature encoding layer. Vox feature encoding layer has one pillow feature net, one PFN layer. So the input of the points feature previously the input feature has 4 features, X, Y, and the intensity. Now they do the extend to 10 features. This is also mentioned in the paper. How they extend X, Y, Z intensity, right? They add the calculate the points mean, all the points, lighter points, then relative to the points mean. They also calculate the center of the pillow, relative to the center of the pillow. Total together, they have 10 features. So actually, it becomes the so the original Vox feature is the like 14 around 14K, 32 times 4. Now it becomes 32 times 10. 10 is now the extended feature by adding some relative distance to the pillow mean and the pillow center. So they become 10 features. Okay, then this extended 10 features go to the PFN layer. The PFN layer is like a linear layer with 64 elements. So we can take a look about this the whole process. This is a PFN layer in the forward part. This is input. 32 times 10 is already extended the dimension. They go to this linear layer. The linear layer definition is just the in channel, outer channel. In channel is 10, outer channel is 64, right? So after this linear layer, so the size, the 10 feature becomes 64. What's this 32 means? Any students still remember? What's this 32 means? What this 32 means? This is the number of the pillow, right? What's this 32 means? This 10 is the feature. What's this 32 means?
It's the maximum number of points in voxel.
Very good, very good. Yeah. So this is the maximum of the points. This is for individual or ladder points in one pillow. Now this is 10 feature. After the linear layer becomes 64 feature. Now then they do a permute, change it. Then they apply the normalization, batch normalization one dimension. Then the loop. So the sizes are the same. Then they apply a touching max operation. Touching max operation is for this dimension. So the result is become the number of the pillows and a 64 feature. Then finally squeeze, remove this channel. So it becomes 14K times 64. 64 is the vector of the feature size. This is the number of the pillow. Why this step? It just one student mentioned that this 32 is for 32 LiDAR points inside the pillow. But we need a feature representation for the whole pillow, not the individual LiDAR point. For example, this vector is for every point that they have 64 channel. Every point has 64 channel. That's for individual LiDAR points. Then you do this max operation. From 32 LiDAR points, you only get one max operation. That means that you using the max operation to get the feature representation for the whole pillow, not the individual pillows. That means you compress from 3 dimension to the 2 dimension using this max operation. Now that's why after you do the max operation, the dimension size. So the linear layer, you change it from DPN to CPN. D is dimension, C is the new channel 64. Right. Then finally, CPN, the max operation from CPN to C and P. C is the channel, P is the number of the pillow ID. CNP. So this is Vox feature encoding layer. Now if you go back to this diagram, now you understand what's the step. DPN to CNP, how you get this feature representation. That's actually straightforward, right? And you can go back to the description. This is followed by a max operation over the channels to create the output tensor CNP. Only read the text, you have no idea, right? But if you match it with the code, you know how they do it. Maximum over all the points, because you don't need to every point representation. You need one pillow has one feature representation. So that means this is pillow ID. Every pillow has 64 channel as a feature. So this is exact same like in this step. This is your learned feature. Then you have next step. After you have the learned feature, once encoded, right, the feature are scattered back to the original pillow location. In the original data, we also have the pillow's original index and the original location in the original 3D space. So you map it to this feature, the same feature, map back to the original C, H, and W. H as height, width, and the channel. You map it back to the original point pillow, the 3D location. C are the same, is a channel, because you know every pillow has the C number of features. In overcode is 64. This is height and width. That's in the original like a 2D view of the point cloud. This is like a bird's eye view. So H indicates the height and the width of the actual cameras. So what's the step in the code to map back to the original the pillow space? So we have this point pillow scattered back. So input is a pillow feature. This pillow is the number of the pillows and the 64 as a channel. We also have the original coordinate. The coordinate for the pillows. Also number of the pillows and the Z, Y, X format, and they have 0 in the front. That's why they have the 4. Now this is the every pillow's coordinate, original coordinate, and that's why we pass in. So what we do is we generate a special feature, the create new. Special feature is like this bird's eye view feature. Channel bird's eye feature is 64. Because here we have 64 feature, and that's the same thing. Then grid size. Grid size is the 3D space, Vox cell, and next time number of X, number of cell in the X, number of cell in the Y, and number of cell in the Z. Because it's a Vox, that's why number of Z is 1. Then the grid size, we actually can create a special size is 64 times this number. And the actual grid size is 432, 496 times 1. 1 is NZ. How we get the 432 and the 496? Any students know how we get this number? Because in our definition, we have X LiDAR range 0 meter to 69 meters, Y range, and Z range. And in our set file, we have Vox size 0.16 meters, 0.60 meters. And in the Y size is 4 meters. Then we can use the meters divided the Vox cell size. We can know the number of the X, number of the Y, and number of Z. Number of Z is Y. So this is actually the whole 3D space divided by the Vox cell. That's why we have the total grid size like this. Then the feature size is 64. So the special feature 3 dimension is like this. This is the channel C. This is the P, index P. How many number of the pillow you have? Okay, then we calculate the index based on the original ZYX format for coordinate. Now we can calculate the pillow's index. then based on this location index, we send the pillow data back to the spatial feature. This is sending to the original space. Then we resize it. So change the batch spatial features become, this is batch size. If we have one batch, times 64. This is channel C, and this is the size. This is the actual size. Or this is actually in the this is my, this is nx, c, y, x size. So match to this one is c, y, and height. Yeah, so this is the feature we get. So we can actually verify. This is the pseudo image we get. The C is 64. Y and height is the number of the grids in the Y dimension and the height dimension. And this is in the X dimension and the Y dimension. This is like a pseudo image. Then next step, we can go to the backbone 2D CNN. Okay, any question for this pillow feature net? How we get this pseudo image? Now we match to the diagram and with the actual code. Any question? Okay, now let's take a look about the backbone 2D. Backbone 2D is very similar to the FPM. They have convolution, lower dimension, right? And this architecture is very similar used in the VoxNet, Apple's VoxNet, right? They do the deconvolution, then concat together. Then they do the detection header, go to the detection header. They're using the detection header similar to SSD. Now, the backbone is like this. Now, this is the same backbone, similar backbone used in the like the VoxNet. Yeah, now let's take a look code, right? So the input feature is batch size, 64 channel, N, Y, and X, right? So there are several defined models in the base BEV backbone. For example, this convolution 2D block stride equals 2 is convolution 2D block. We represent like this. This is another convolution 2D block. This is 64 to 64. This is 100 to 120. Stride 1 to 1, 3 times 3 kernel. Now, we also have deconvolution. Now, convolution transpose 2D. 64 to 128. Now we call it this convolution transpose 2D module. Yes, because like here we also have the deconvolution over here. Based on this code module, we can see the block 1 definition. Block 1 is we have 3 convolution 2D block over here. We also have 1 deconvolution block. We also have the block 2. Block 2 here we have 5 convolution block. This is block 2. We also have the deconvolution block. We have the convolution we use in the PyTorch convolution transpose 2D to implement the deconvolution. Then we have the block 3. Now this is block 3 is a simplified block. Okay, then we also have the deconvolution block 3. This is the deconvolution block 3. And now we have the block 1, 2, 3 and deconvolution block 1, 2, 3. And now we need to point them together, piece them together. So this is the actual architecture in the code. This is input feature. Go to the block 1, go to block 2, go to block 3. And this is size change. Go to the first block. The channel size are the same as the resolution, like the image resolution, right? Is divided by 2, right? Then block 2, the channel become 128. Because stride equals 2, here stride also equals 2. It's also a downsample. Downsample go here. Then go to block 3. Channel become 256, right? Image size stride 2, downsample to 62 and 54. Now, then every output goes through the deconvolution, and the deconvolution. So this size goes to the deconvolution, is become 128 channel resolution are same. This one do upsample 2 times, so the resolution become 248, 212. This one upsample 4 times. Now deconvolution 4 times, you get the same size. And now you concat them together. So the resolution is 248 times 216. Channel number is 384. This is the backbone output. Okay, after the backbone output, now this is the backbone's output called the spatial feature 2D. Now we go to the last module, anchor head single. So this is a detector. And as we go to the 3 modules, convolution 2D for convolution classifications, convolution bounding boxes, and convolution. What's this? What's this header? Any students still remember?
Direction classifier.
Very good, very good. Direction classifier, 3 branch. This is a simple convolution 2D, convolution 2D. Then this is get the size, the size. Then do the permute, change the channel number. It become 248 times 216. Why the 16 is actually 3 times 6. The 3 times 6, where it's coming from? It's a number of anchors per location times number of classes, because Kitty has 3 classes. The number of anchor per location is 6. That's why for classification they have 18. And they have 18. For bounding box 2D, bounding box 2D, the bounding boxes, they have 7 elements, and the number of anchors per location also 6. That's why it's 6 times 7. That's why it's 42. Direction is easy, right? That's why it's only 2. That's why it's 6 times 2. That's why it's 12. Then they go to the generated predicted box header. Then generated predicted box header, they will output this classification and the bounding box. So this is generated box predictor. This 3 means classes. This 3 means X box dimensions. Why this number? This number is 248 times 216 times 6. This is the total number of the boxes. So this is generated predicted box output. Then finally, this batch classification predicts batch boxes predicts. The classification boxes go to a sigmoid function. So dimension are the same. Then they also get a max operation. Get the classes. Then finally, they also go through the non-maximal suppression to remove some duplicates, or do some filtering, because it's like a one-stage detector. So non-maximal suppression is very, very important, because there are lots of the duplicate bounding boxes. Then after filtering, this is the final output: 35 times 7 for predicted boxes, 35 for scores, and 35 for the labels. And if you do visualization, this is all the bounding boxes output. So this is the whole process. Okay, any question for this point pillow process? This is the detailed process, how they do the mapping and how they do the detection. And the last, the non-maximal suppression is also very critical. So otherwise, they have so many boxes. Okay, any question? So hope this process help you to better understand this kind of diagram. So understand what is the point pillow, and this is really a very good representative work. Okay, so this second set is a kind of the box representation or pillow representation based work. There another point of set of work is directly operate with the points. This has lots of the mathematical foundation, right? That means they need to design a new operation similar to the convolution 2D, but it's for the 3D points. And they're using many mathematical features, is like input-wise permutation invariances. Because if you do the permutation for the points, does not impact any of these results. So this result is actually coming from Stanford. So the first one is point net. Point net is used for classification, classify individual point for what's the classes, or to segmentation. Segmentation is extension of the classification. Then they also have the point net plus. Then they have IPOD. This is a point-based object detector for point cloud. Utilize the point net to do the 3D object detection for the point cloud. Then the key idea of the point cloud is like they want to utilize one mathematical feature. If you change the order of the points, does not change anything because the 3D representation are the same. So mathematically, any continuous input-wise permutation invariance function f, they can be approximated by the composition of the two functions h and g, h function and the g function. So the point net has lots of the mathematical foundations over there, right? And but you can see like this process is like s, y, z, and the intensity after this process, you can get something like embedding. Using this point net kind of mathematical operation, get the embedding. So this is the key thing of the point net. Now this is operation for individual point. You can get the feature for individual point. Okay, so now go to the 2018, right? There's one famous paper called Frastrom point nets for the 3D detection. So this is the lead author of the point net and the point net plus extend to the 3D object detection area. You can check their code in the Frastrom point nets. What's the Frastrom point net did is, right? They augmented the point net with a 3D region proposal network, because they need to partition the 3D input scene into different subspaces. Then each subspaces can have the ladder points that they can classify into the class. So what they do is, but there are also challenges, right? How to localize object in the large scene scale. Because point net is individual point operation, but if you want to go through the whole thing, that's too complex. So if you go to a very cropped region for a car, and now they can classify this point maybe belongs to a car, this point maybe belongs to a background. But the first step is how to crop the car from a larger scene. This is a challenge. So Frastrom point net using a very simple approach. Based on RGB image, image-based 2D detector. Let's see, there's object over there. Then they do a Frastrom proposal because the image has something there. You can do a Frastrom proposal, something like this. Maybe this region, this Frastrom 3D space maybe contain the car's 3D points. So using 2D images results to get the region of the points. Then using this ones to do the instant segmentation to say, oh, this is the actual car's points. Other points are not belongs to the car. Then they can approximate the 3D bounding boxes. This is almost the representative work, right? How to apply the point net for the 3D detection process. This is from the leading author of the point net. But from this process, you can see this is very limited by the 2D detection. If in the 2D detection you miss this object, then this one can't work. So this one is like a very primitive work, so it's pretty limited. But the good thing is this one has also official implementation, and the result is also okay. It's pretty good, right? You can get a Frastrom using the image, right? Map to a region, 3D frustration region, then crop the points. Get the actual points belongs to a car, then get the bounding box. Then based on this 3D, and they also test. This is their tested. This is their tested the results based on the key data set. The results also is pretty good. Yeah, but this is in some very high density area with lots of the overlapped persons. The result is not that good. It relies on the 3D proposal, 2D image to generate the 3D region to do the proposal. If this 2D detection is not accurate or have some overlap, they have some challenges. Then another interesting work, right? It's actually better work. It's called the point RCN. This actually has a better solution than the previous frustral point net. Right? So instead of using RGB images to generate the proposals or maybe do some projection, right? They're using a stage 1 subnet directly generate high quality 3D proposals from bottom up. It means that they just generate the 3D proposals. Then they have stage 2 subnet transfer the points for each proposal to candidate to learn better special feature. The architecture is learned from the fast RCN. That's why it's called the point RCN. The process is like frustral is using image detector. What they did is get the 3D proposal. So for example, they do the point cloud representation. This is segmentation kind of the work. They get the point-wise feature vector for every point. Then for this one, they separated the 3D beam-based 3D box and foreground point segmentation. They do a rough segmentation over here. But this is just a 3D proposal. Now there are lots of the proposal boxes over there. But then using this results, right, get semantic local spatial features. Then using point net to fine-tune, to refine the boxes, they can have some better results. So this is the point RCN based work, 2-step. So make the results, the accuracy is actually better. And internally, they utilize the point net purpose, especially for the segmentation part. Okay, so previously we talked about some of the LiDAR only based solution, right? There are also some approaches they can do the LiDAR and image fusion. There are some famous work. For example, one is called MV3D. So MV3D is a pretty interesting fusion approach, right? Because the LiDAR has multiple bird's eye view, height maps, densities, intensities, right? Also, LiDAR also can have also front views, right? Then you have image, RGB. This is your input. How to use this input to the fusion process, right? But they still also do the mapping process, right? They're using both bird's eye view, front view, and the RGB image. Yeah, so their network looks very fancy, but they basically, you can see they utilize bird's eye view to generate the 3D proposals for the front view proposal and the image proposal. So that means their fusion is actually in the proposal stage. Then let the front view go to convolution layer, image view go to convolution layer, right? Then after this kind of 4 times deconvolution, RY polling, and this front views feature, they integrate them together to the fusion process. Then finally, how the multi-class classify and 3D bounding box regressor to get the 3D bounding box. It's like using multiple LiDAR map to multiple image view and using the images to do the fusion process. This is the MV3D. Yeah, MV3D here they mentioned some of the fusion process. But for example, they have multiple channels over there. They do multiple fusion. They call it deep fusion process. So compare with early fusion and the late fusion. They think this fusion is actually works better. They do the fusion for multiple times. Yeah. So yeah. And the MV3D also don't have the official implementation, but there are also the third-party implementations. So and you can see the results are also pretty good. Yeah, another famous fusion-based solution is called AVOD. It's called Aggregate View Object Detection Network. So instead of using multiple image view, they use the image view, bird's eye view from the LiDAR, and a 3D anchor grid. So bird's eye view extract feature, image view extract feature, but then they do the one convolution, right? So anchor will crop and resize this feature, then do the fusion. That for the bird's eye view, do the same, crop and resize, do the fusion process. Then go to the fully connected layer, do the non-maximal suppression. But this kind of fusion is only used to get the proposal. So now you get the key proposal for the image feature map. Also get a take proposal for the bird's eye view feature. Then this two crop and resize, they do fusion again. Get the then go to the fully connected layer, then do the non-maximal suppression. Finally get the detected object. The good thing for AVOD, they have the official implementation. Their fusion process is very interesting. They're using this 3D anchor grid to get the proposal. Then they do the fusion process. Okay, any question for the MV3D and the AVOD? So AVOD, so we have one. Yeah, so this is they have the one of the detection results over there, right, in their also paper. So AVOD is also a very famous approach for the camera and the LiDAR fusion process.